Okay, so this is section 16.2b, video number 2. So last video, we basically developed how we're going to be able to determine the amount of work done over a vector field using line integrals. So the equation that we ultimately came up with was the line integral over c of f dot dr, where dr is just r prime of t dt. Everything has to be parametrically defined in order to do it. Okay, so now we're going to look at, so example 1, let f be the vector field shown in the figure below. If C1 is a vertical line segment from -3 to -3, +3, determine whether the line integral of f dot dr is positive, negative, or 0. So the first thing we should probably do is draw that line segment. Let's sketch it in there. So from -3, -3, looks like it's down here in this corner, to -3, +3. So it's basically this vertical line which goes straight up to there. That's our vertical line segment. We want to determine whether the line integral is going to be positive, negative, or 0. So basically, is our vector field helping or hurting in our direction? Well, if you look at this, all of these vectors, because they're in what looks to be a counterclockwise circular rotation, as we go up the orange line, every single one of those is generally in the same direction. Yes, some of them are off like at an angle, but nothing is completely perpendicular, because perpendicular would neither help nor hurt. But everything seems to be generally going in the same direction as the orange. So we would say that this would have a positive outcome on the line integral. It looks like it is helping our path. So now let's see if we take C2, which is the counterclockwise oriented circle with a radius of 3 and the center at the origin, determine whether the line integral of f dot dr is positive, negative, or 0. So if we basically have a radius of 3, that means you're going to be hitting all of these values right here. And it says it's counterclockwise, so it's going this direction. Okay, for lack of being able to draw a better circle, this isn't horrible. But the big thing is the arrows are going this direction. That is the way that the path is being traversed. Well, it should be relatively obvious that we are going exactly against the vector field. So in this case, this would be a negative line integral, because it is hurting. It is going exactly against us. The vectors are in generally the opposite direction, it seems like, the entire time. So hopefully that concept there makes sense. As a matter of fact, let me kind of erase just a little bit of this, just to show that this was the general direction that we were heading. But I hope that makes sense. So what you're really looking for is, in our general direction, what seems to be happening? Does the vector field seem to be helping or hurting? So it is good to, have a sketch of the vector field if you're going to be doing it based upon that kind of information. All right, the rest of these examples are actually going to be algebraic. So we'll know by the result whether we had something which was generally helping or hurting, but whether it's a positive or negative value. Okay, so let's evaluate the line integral of f dot dr, where c is given by the vector function r of t. Okay, so in order to do this, let's go ahead and write our equation up here. So we know it's going to be from t1 to t2 of f dot dr, which is the same thing as f dot r prime of t dt. Remember, r prime of t dt is dr. What do we need? Well, we are going to need our function, our force, parameterized at x of t, y of t, z of t, but there's no z here, so it's two-dimensional. So we'll just go with f of x of t, y of t. So ultimately what that's going to give us, let's see, it tells us that t goes from 0 to 1. That's nice. We don't have to figure that out. Of our vector function of f, parameterized, dotted with r prime of t dt. So we need to figure these things out. So the first thing is, let's define our f function parametrically. Well, let's see. Our force function is given to us as x squared y cubed I minus y square root of x j. Seems to me like the easiest thing to do here would be to probably define this. Well, actually, in this case, it gives us r of t. Never mind. We don't even have to do it. If you look at r of t, it tells us what x and y are, because the x component is the t squared I. So x is going to be t squared. And the y component is going to be the negative t cubed. So we don't even have to worry about it. It's defined it for us. Great. But now we do have to plug those things into our force function. So we're going to get the integral from 0 to 1, defining our force parametrically. So that's going to be x squared, which is t squared squared. So that'll be t squared squared, times y cubed, which is going to be negative t cubed cubed. Okay, that's the first component. And then the second one is, let's see, minus y square root of x. So it's going to be minus y minus a minus t cubed is going to be t cubed. And then the square root of x, well, that's the square root of t squared. There's our force as parametrically, defined parametrically, excuse me. And then we need our r of t function, r prime of t function, excuse me. R of t is t squared negative t cubed. So r prime is going to be 2t negative 3t squared dt. All right, let's go ahead and clean up our force. I wrote it out this time. Normally you could probably do some of that in your head. So let's see, t squared squared is t to the 4th. Negative t cubed cubed is t to the 9th. So t to the 4th times negative t to the 9th is going to give us negative t to the 13th. And then we've got t cubed times the square root of t squared, which is just t. So we've got t to the 4th, dotted with 2t negative 3t squared dt. All right, so dot product, multiplying the first components together, we're going to get negative 2t to the 14th. The second components together, we get minus t to the 6th. And remember, we add these. So it's no longer a vector once you've taken the dot product. So let's see, you can't really add those together. So the only thing we can do is go ahead and evaluate the integral at this point. All right, it's going to be some messy numbers. So let's see, it's going to be negative 2/15 t to the 15th minus 1/7 t to the 7th. Yuck, that means we're going to have to find least common denominator of 7 and 15, but we'll handle it. Evaluated from 0 to 1. The nice thing about this one is that the 0 makes everything go to 0. So let's just plug in the 1 and we get negative 2/15 minus 1/7. Let's see, 30, no, 45, 60, no, 75, no, it's going to be 15 times 7. 15 times 7, I believe, is 105. So these will both be over 105. So the first one's going to get multiplied by 7, so that would be 14. Forgot my negative. And the second one's going to get multiplied by 15, so we're going to get 15. So it looks like we're going to get negative 29 over 105, which, because this is negative, tells you that in general or overall along this path, your vector field actually was working against the path of your motion, because you ended up with a negative overall amount of work. So that's what that's indicating. All right, mathematically, these are not extremely challenging usually in the beginning here, but they can, obviously, you can make very easy mistakes. So If I make one, hopefully you guys will catch it, hoping not to make any mistakes. All right, example number 3. So again, we're going to evaluate the line integral of f dot dr, where c is given by the vector function r of t. Okay, they've given us the t bounds, which again go from 0 to 1. Our force is sine of x, cosine y, xz, and this is 3-dimensional in this case. So let's go ahead and define. It might be easier if you just stick with defining x first. So x is going to be t cubed, y is negative t squared, and z in this case is t. Again, that's coming directly from my r of t function. Okay, so that's where that's coming from. Now we need to define our vector parametrically. So we need to redefine the vector part parametrically. So we're going to get the integral from 0 to 1. All right, so the x component is sine of x, but x itself is t cubed. So we're going to get sine of t cubed. The y component is going to be cosine of y, which is cosine of negative t squared. And then the z component is going to be xz. So that's going to be t cubed times t, which is t to the 4th. So there is our function vector. Excuse me, I keep saying function. Our force vector defined parametrically, dotted with r prime of t, which is dr, right? Dr is r prime of t dt. So the dr part, or the r prime of t, is going to be the derivative of t cubed, which is 3t squared. The derivative of negative t squared is negative 2t, and the derivative of t is 1 dt. All right, let's go ahead and perform the dot product. So we're going to get 3t squared sine of t cubed plus, or in this case, minus 2t cosine of negative t squared plus t to the 4th dt. Now we are in a position that we can take antiderivatives. Technically, you should probably split this into multiple integrals. I think at this point in time in your calculus careers, you are probably able to see how this is going to work. We're going to do a u substitution on both of the first 2 terms. The last term will be very easy antiderivative. So let's let u, in this case, be t cubed, making du 3t squared dt. So then dt is du over 3t squared. For the middle piece, we're going to let u equal negative t squared. So du then will equal negative 2t dt, and dt would then equal du over negative 2t. And this is wonderful because both of the coefficients are identical to what we got for these things, so it's going to make those go away. So ultimately, what we're going to be taking here is, in the first one, we're going to be taking the antiderivative. Once you make all your substitutions, the 3t squareds are going to go away. You're going to take the antiderivative here of sine of u du. And in the middle piece, when you make all your substitutions, u goes into the cosine part. So then you'll have a negative 2t crossing off the negative 2t from the dt part. So you get cosine, and this is going to be plus cosine of u du, and then we'll still have the t to the 4th to deal with. All right, I did not change the bounds in this one. I think we're just going to leave it so that it's all 0 to 1, so I'll change everything back at the end here. So if I take the antiderivative of sine, it's negative cosine. The original u for that one was t cubed. If I take the antiderivative of cosine here, it's going to be sine. The original u for that one was negative t squared. And then the antiderivative, bringing that all the way down, of t to the 4th is going to be 1/5 t to the 5th. So there's my antiderivative. We're going to evaluate that from 0 to 1. All right, remember that 0 will not necessarily make everything go away here. So if I plug a 1 in, we're going to get, geez, what is this? Negative cosine of 1, whatever that is, plus sine of negative 1, whatever that is, plus a fifth, minus, plugging in a 0. I do get cosine of 0, which is 1. So we get negative 1 out of that. Sine of 0 is 0, so that's gone. And then a fifth of 0 is still 0. So the only piece that actually gave us anything there was that extra cosine part. So let's see, what are we going to get here? We're going to get the negative cosine of 1 plus the sine of negative 1. And then we get a fifth minus minus 1, so that's plus 1, so that's going to be 6/5. Okay, now that technically is the answer. You might also see it, if it was like in a book or something, you might also see it written this way. Minus sine of 1, and no, you're not factoring out the negative from the angle. You can't do that. That's a property, however, of the fact that sine is an odd function. And an odd function for sine means that sine of a negative angle is the same thing as the negative sine of the positive angle. So it's a way to simplify it so you don't have a negative angle, that's all. And just so that we know, I'll put this in there as well, that an even function would be like cosine of negative theta is the same thing as the cosine of positive theta, and that's because it's symmetric to the y-axis. So plugging in a negative or a positive value for your angle will not change the value of the cosine. Cosine is an even function. Just so you know, tangent is also an odd function if it ever comes up. This is more than likely the way you would leave the answer, and I'm perfectly fine with that. All right, I think we've got one more to go. Yep, this is the last one. So find the work done by the force field given as force is y plus z, x plus z, and x plus y on a particle that moves along the line segment from 1, 0, 0 to 3, 4, 2. All right, so they did not specifically give us r, but we can develop r because what we've got is a line segment. So our r of t is going to be basically that line defined parametrically. So the x part, remember this is going to be the equation of a line in parametric. So x starts at 1 and goes to 3, so that's an increase of 2t. The y part starts at 0 and then increases up to 4, so that's just 0 plus 4t, or just 4t. And then the z part starts at 0 and goes to 2, which is going to be 2t. So there's your r of t defined parametrically. And remember, it's a line segment, so t is going to go from 0 to 1. It will always be that way. And technically, you can make it go 0 to whatever you want to, but there's really no point in doing that. 0 to 1 is the easiest way to go. We have to define our force parametrically. So the force is y plus z. Well, let's see. Y is 4t, z is 2t. If I add those together, I get 6t. The y component is x plus z, so it's 1 plus 2t plus another 2t, so that's 1 plus 4t. And then the z component is x plus y, so that should be 1 plus 6t, it looks like. So now that the force and the position function are both defined parametrically, I'm going to dot the two of those, and we'll take the integral. So our integral will go from 0 to 1 of force 6t, 1 plus 4t, 1 plus 6t, dotted with 1 plus 2t, 4t, 2t, dt. All right, let's see what we get. Let's dot these things. So we get 6t plus 12t squared, 6t plus 12t squared, plus, let's see, it's going to be 4t plus 16t squared. And then the last piece is going to give us 2t plus 12t squared dt. Let's combine all our squared terms. So we're going to get 12 plus 16 is 28, plus 12 more is 40, so we get 40. Did I do that right? Yeah, something's not right. What did I do wrong? Okay, geez. Hopefully you guys didn't copy all this and you caught my mistake. If not, sorry, pick out your erasers. This is not right. The force is perfectly fine. It has to be defined parametrically. This has to be r prime of t, not r of t, r prime of t. Makes this actually quite a bit easier because r prime is going to be 2, 4, 2. I knew something wasn't working out right because I shouldn't have ended up with any squared terms left over in the integration here. So now let's go ahead and do this. So that's going to be 12t plus 4 plus 16t, so 4 plus 16t plus 2 plus 12t. Yeah, that looks much, much better. So now we're going to take the integral from 0 to 1. Let's see, 12 and 16 is 28, and 12 more is 40, so 40t. The constants are going to be 4 and 2, so plus 6 dt. Antiderivative, so that's going to give us 20t squared plus 6t. Evaluated from 0 to 1, this is going to work out very nicely. So you get 20 plus 6, which is 26, minus 0. We get a total work done of 26. So this one definitely helped us in our path along this curve. All right, that is it for this section. So that should be plenty enough.